Imagine standing in a completely dark room. You cannot see the walls. You cannot see the floor. You reach out your hand and feel nothing. You take a step forward and feel nothing. You keep walking and the darkness just continues in every direction with no end and no boundary and no wall to push back against your outstretched fingers. That is what space is. Not the pretty space you see in textbook illustrations with colourful planets lined up like beads on a string. Not the glowing nebulae in NASA photographs that look like paintings made by the universe itself. Not the comfortable, manageable, diagram-sized space that fits on a poster in a classroom. The real space. The actual space. The space that exists outside the thin shell of air wrapped around this tiny world you are sitting on right now. The space that would stop your mind completely, that would cause something inside your brain to simply shut down and refuse to process what it was being asked to understand, if you truly grasped it for even one unguarded second. And tonight, we are going to grasp it. Not just think about it. Not just hear numbers that slide off the brain like water off glass. We are going to feel it. We are going to walk through it at a scale your body can recognize, using distances your legs have covered, using objects your hands have held, using the kind of spatial understanding that billions of years of evolution built into your nervous system, long before any human being ever looked up and wondered what those lights in the sky actually were. By the time this journey is over, you will not think about space the same way again. Not because I will have told you something revolutionary. The facts we are going to cover tonight are known. They are measured. They are confirmed. But knowing a fact and feeling a fact are two entirely different experiences, and tonight we are going to do the second one. So before we go anywhere, I want you to do something simple. I want you to look at your hand. Hold it up in front of you if you can. Look at the palm. Look at the lines running across it, the fingerprints, the way the skin folds at the knuckles. This hand is your entire physical experience of the world. Everything you have ever touched has been through this hand or one like it. Every texture, every temperature, every surface that has ever felt real and solid and present to you, it all came through here. This hand is your body's primary instrument for understanding that things exist and have dimension and weight and presence. Now I want you to imagine that this hand is holding the sun, not a model, not a photograph, the actual sun, the star at the center of our solar system, the thing that is 1,300,000 times the volume of the Earth. The thing that contains 99.8% of all the mass in our entire solar system. The thing that has been burning hydrogen into helium for 4.5 billion years and will continue doing so for another 5 billion years before it swells into a red giant and swallows the inner planets whole. I want you to hold that in your hand like a basketball right now. If the sun were a basketball sitting in your palm, do you know where the Earth would be? Take a moment before I tell you. Take a guess. Picture the solar system in your head, the way you have seen it in diagrams your whole life, and make a guess about where the Earth would be if the sun were a basketball you were holding. Most people guess somewhere between 1 and 5 meters. Arm's reach, maybe. Across a room at most. The Earth would be a grain of sand. Sitting on the ground, 30 meters away from you, not 30 centimeters, not 30 feet, 30 meters, the length of 3 buses parked end to end, 3 school buses bumper to bumper. You would need to walk across a basketball court and keep going to reach it. And when you got there, after that long walk through the empty space, you would need to get down on your hands and knees and search the ground, because the Earth on this scale is not just small, it is a single grain of sand, invisible unless you know exactly where to look. That grain of sand is your home. Every mountain you have ever seen in a photograph, every ocean you have ever stood at the edge of, every city you have ever walked through, every forest and desert and river and plain, every person you have ever loved, every meal you have ever eaten, every conversation you have ever had, every dream you have ever dreamed, every moment of joy and grief and confusion and clarity you have ever experienced is contained on that grain of sand sitting on the ground 30 meters from a basketball. Everything that has ever mattered to any human being who has ever lived is on that grain of sand. And that grain of sand is so small that if you sneezed at the wrong moment while setting it down, it would be gone. Now I need you to understand something before we go any further. I need you to understand why most people, when they hear these numbers, feel nothing. Why the scale of space is so consistently, stubbornly impossible to feel, even when someone is actively trying to explain it. The reason is that your brain did not evolve to feel these scales. Your brain evolved over millions of years on the surface of a specific planet to track specific predators across specific distances, to find water within a day's walk, to navigate a forest, to judge the weight of a stone before throwing it, to estimate whether a gap is jumpable. Your brain is a survival machine built for a very specific range of scales, and the scale of the universe falls so far outside that range that your brain simply cannot generate the emotional response that the numbers logically demand. When you hear that the sun is 1,300,000 times the volume of the Earth, some part of your brain just says large and moves on. It cannot feel large. It can only think it. And thinking it and feeling it are completely different experiences, with completely different impacts on how you understand the world. So everything we do tonight is an attempt to trick your body into feeling what your mind cannot. We are going to use human scale distances, things your legs have walked, to represent cosmic distances. We are going to use objects you have held to represent things you could never hold. And we are going to do it slowly, step by step, layer by layer, until something shifts inside you, because it does shift. I promise you it shifts. There is a moment in this journey, and it comes at a different point for different people, where the numbers stop being numbers and become something physical, where your body actually registers the weight of what you are understanding. And when that moment comes, it stays with you. You carry it with you after the screen goes dark. You feel it when you go outside and look up at the night sky. You feel it in a way you never felt it before. That is what tonight is for. Let me know in the comments when that moment comes for you. Just write a timestamp if you want, or just write the word felt. I genuinely want to know where in this journey the scale becomes real for different people. It is one of the most interesting things I have ever tracked across comments on a video like this, and I find myself reading through them for hours after I post. Alright, let us continue walking. We left Earth. The grain of sand is 30 meters behind us, invisible already in the dust. We are walking away from the basketball sun toward the outer planets. We have 4.5 billion kilometers of real space to cover, which on our model means we have some walking to do. First stop, Mars. Mars, the red planet, the world that has occupied more of humanity's imagination over the past century than any other place in the solar system. The world that science fiction writers populated with ancient civilizations and canal builders and dying races and invaders. The world that we have now mapped more thoroughly than many parts of the Earth's ocean floor. The world where our rovers have driven and our helicopters have flown and our landers have listened to the wind. On our scale, Mars is another grain of sand, smaller than the Earth grain, sitting on the ground 50 meters from the basketball's sun, 20 meters further than the Earth. That gap between Earth and Mars, the gap that our best spacecraft take between 6 and 9 months to cross, depending on the orbital alignment at launch, that gap is about the length of 2 school buses on our scale. 20 meters of empty nothing. 6 weeks of preparation and 9 months of flying at incredible speeds through total darkness to cross what amounts to 20 meters on our model. We sent robots across that gap. We sent robots the size of small cars, packed with scientific instruments, powered by plutonium or solar panels, loaded with cameras and spectrometers and drills and weather stations, and we flew them through that 20-meter gap at 60,000 kilometers per hour and landed them gently on the surface of that smaller grain of sand, and they drove around taking photographs and drilling into rocks and measuring the chemistry of the soil for years. And when those robots drive across the surface of Mars, they are sending their data back across that gap. Radio signals traveling at the speed of light, and even at the speed of light, those signals take between 3 and 22 minutes to arrive, depending on where Earth and Mars are in their orbits. When the Perseverance rover encounters a problem and sends a distress signal, the scientists at Mission Control have to wait up to 44 minutes for a round-trip communication. 22 minutes for the signal to arrive. 22 minutes for their response to get back. This is what it means to operate across space. Even the shortest distances in the solar system impose delays that make the word communication feel strange and stretched. Jupiter. After Mars, the solar system opens up. The inner solar system, the region containing Mercury, Venus, Earth, and Mars, is actually a relatively compact region compared to what comes next. Between Mars and Jupiter, there is the asteroid belt, a region containing millions of rocky objects ranging from dust particles to the dwarf planet Ceres, which is about 945 kilometers across. The asteroid belt sounds dense and dangerous when you hear about it, the way it sounds in movies where ships have to dodge tumbling boulders. In reality, the asteroid belt is mostly empty. The average distance between objects is hundreds of thousands of kilometers. If you flew a spacecraft through it, which we have done many times, you would probably never get close enough to an asteroid to see it with the naked eye. But Jupiter is something else entirely. Jupiter is the largest planet in the solar system. It is more than twice as massive as all the other planets combined. It is a gas giant, a world with no solid surface, just layers of gas and liquid getting denser and hotter as you go deeper, with a possible rocky core at the center that we have never been able to directly observe. Its atmosphere contains storms that have been raging for centuries. The Great Red Spot, a storm larger than the entire Earth, has been spinning continuously for at least 350 years since humans first observed it, and possibly much longer. The winds at its equator blow at 500 kilometers per hour. It has at least 95 moons, including Europa, which has a liquid water ocean beneath its icy surface and is one of the most compelling candidates for extraterrestrial life in the solar system. Jupiter is a world that defies every intuition built by living on Earth. There is no ground to land on. There is no surface to stand on. You would just fall through layers of increasingly dense gas and liquid until the pressure crushed you into something unrecognizable. And you would fall for a very long time. On our scale, Jupiter is a marble, a small glass marble about the size of the ball bearing inside a ballpoint pen, sitting on the ground, 150 meters from where you started. You would need to walk the length of 1.5 football fields from the basketball sun to reach a marble. And in between, nothing. Absolute nothing. No other objects, no halfway points, no rest stops, just empty, dark, silent, cold nothing for 150 meters. This is the gap that the Pioneer and Voyager spacecraft crossed in the 1970s and 1980s. This is the gap that the Galileo spacecraft crossed to enter orbit around Jupiter in 1995. This is the gap we crossed with machines we built using mathematics developed over centuries, using computers less powerful than the phone in your pocket, using launch windows calculated to the second to take advantage of planetary alignments that would save fuel and time. Are you starting to feel something yet? Because I want to check in with you here. We are still inside what most people think of as the solar system. We have not even reached the middle of it yet, and already we have walked 1.5 football fields from a basketball and found nothing but a marble. Drop a comment right now if this is landing differently than you expected. I want to know where people are emotionally at this point in the journey. Just write a number, 1 through 10, for how real the scale is feeling to you right now. 1 being, I still feel nothing, and 10 being, I think I actually feel it. Let us see what numbers come up. Saturn. Of all the planets, Saturn is the one that produces the most consistent reaction in people who see it for the first time through a real telescope. Not a photograph. A real telescope eyepiece in a real backyard or observatory with the real planet floating in the real sky. People gasp, grown adults, scientists, people who have looked at photographs of Saturn their entire lives and know exactly what to expect. They put their eye to the eyepiece, they see the planet and its rings suspended in the darkness, and they gasp. The rings look so perfect, so impossibly architectural, so much like something painted rather than something real, that the brain resists it. It looks fake, and that resistance, that moment of the brain refusing to accept what the eye is seeing, often produces an involuntary sound. I have seen this happen many times. It never gets old. The rings of Saturn are made of billions of individual pieces of ice and rock, ranging from tiny dust particles to chunks as large as houses. Each piece is on its own orbit around Saturn, moving at slightly different speeds depending on its distance from the planet, all of them together creating the appearance of solid rings from a distance. The rings are enormous in diameter, stretching to hundreds of thousands of kilometers from the planet, but incredibly thin. In most places, the rings are only about 10 to 30 meters thick. If you scaled Saturn and its rings to the size of a pancake, the rings would be thinner than the pancake. On our scale, Saturn is another marble, a slightly larger marble than Jupiter, but still a marble. Sitting on the ground, 280 meters from where you started. You are now more than 2.5 football fields from the basketball sun. The basketball is so far behind you that it has become a small bright point, clearly visible, but no longer obviously a basketball. You have to remember that it is a basketball. From this distance, it looks like a bright star. And that is one of the things that strikes me deeply about this model. From Saturn, the sun is not a warm, face-filling presence in the sky the way it is on Earth. From Saturn, the sun is a bright star. Brilliant, yes. Still by far the brightest thing in the sky. But a star. Not the overwhelming sky-filling source of light and heat that we experience. A distant, intensely bright point of light. If you stood on one of Saturn's moons, the sun would appear about as large as a shirt button held at arm's length, and it would provide about 1% of the warmth it provides on Earth. Saturn is cold. The cloud tops average about minus 178 degrees Celsius. The rings themselves are even colder, and it is still inside the solar system. Still, by cosmic standards, practically in our backyard. Uranus. Uranus is a strange world. it rotates on its side with an axial tilt of nearly 98 degrees, meaning it essentially rolls around the Sun like a ball, rather than spinning upright like a top. The leading theory is that early in the solar system's history, Uranus was struck by an Earth-sized object that knocked it onto its side, and it has been rolling that way ever since. This means that each pole of Uranus spends 42 years in continuous sunlight, followed by 42 years in continuous darkness. The seasons on Uranus are the most extreme of any planet in the solar system, not because of temperature variation, which is surprisingly uniform, but because of the daylight cycle. Uranus is also notable for being the coldest planet in the solar system, despite not being the furthest from the Sun. Its cloud tops can reach -224 degrees Celsius. We do not fully understand why Uranus is so cold. It generates almost no internal heat of its own, unlike the other gas and ice giants. It is just radiating away whatever heat it absorbed, and that is essentially it. The reason for this is still being studied. On our scale, Uranus is a small ball bearing, a very small metal ball, sitting on the ground, 560 meters from the basketball sun. You are now more than half a kilometer from the start. The Sun behind you is clearly just a point of light. If you were not sure where you started, you might lose it against the background. Neptune. The last of the official planets, the most distant, the coldest except for Uranus, the one with the strongest winds in the solar system, with gusts measured at over 2,000 kilometers per hour, fast enough to create sonic booms if there were air on Earth moving that fast. The one that was discovered not by someone accidentally spotting it through a telescope, but by mathematics. Two astronomers working independently used the gravitational perturbations in Uranus's orbit to predict where an undiscovered planet must be. And when telescopes were pointed to those coordinates, Neptune was there. It was the first planet discovered through pure mathematical reasoning rather than direct observation. One of the great intellectual triumphs in the history of science. Neptune takes 165 years to complete a single orbit of the Sun. It was discovered in 1846. It did not complete even one full orbit since its discovery until 2011. There are people alive today who were born before Neptune had gone all the way around the Sun since humans first spotted it. On our scale, Neptune is another tiny ball bearing, sitting on the ground, 900 meters from where you started, nearly a full kilometer from the basketball sun. You have now walked almost a kilometer through absolute emptiness. You have passed two planets that are invisible on this scale, and two that are tiny marbles, and two that are ball bearings barely visible in the dirt. And you have reached the last major planet. And here is what I want you to feel. You are 900 meters from the Sun. In real space, you are 4.5 billion kilometers from the Sun. The light that left the Sun just now will take 4 hours to reach Neptune. If you stood on Neptune and looked at the Sun, you would see a bright star. Bright enough to read by, probably, but not much more. Not warm, not filling the sky, just a very bright star. And from where you are standing, 900 meters from the basketball, it is already just a point of light. Now, most people think this is where the solar system ends. Most people think the solar system is the 8 planets. Maybe throw in Pluto for sentiment. Maybe acknowledge the asteroid belt. And that is the solar system. That is like saying the city is just the downtown area, and ignoring the suburbs, the exurbs, the agricultural regions, the watersheds, the mountains that feed the rivers, that water the fields that feed the city. The city does not end where the skyscrapers end. And the solar system does not end where the planets end. The solar system has an outer structure, a vast, extended, ancient structure that extends so far beyond Neptune that Neptune might as well be in the Sun's living room. And understanding this outer structure is, I think, one of the most important things a person can know about where they live. Let us keep walking. Beyond Neptune, the solar system does not suddenly become empty and then stop. Instead, it transitions into a region we call the Kuiper Belt. The Kuiper Belt is a disc-shaped region of space extending from Neptune's orbit outward to about 50 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, about 150 million kilometers. So the Kuiper Belt extends from about 30 astronomical units, where Neptune is, to about 50 astronomical units. The Kuiper Belt is full of icy objects, hundreds of thousands of them, probably more that we have not discovered yet. Comets, dwarf planets, ancient frozen debris from the formation of the solar system 4.5 billion years ago. Pluto is in the Kuiper Belt, so is Eris, which is slightly more massive than Pluto. So are Makemake and Haumea, and dozens of other known dwarf planets, and hundreds of thousands of smaller objects. These objects are the original building materials of the solar system, the frozen inventory of what was left over after the planets formed, preserved for 4.5 billion years in the cold dark beyond Neptune. On our scale, the Kuiper Belt extends from 900 meters to about 4 kilometers from where you started. You walked a kilometer to reach Neptune, and you thought you had seen the solar system. The Kuiper Belt extends 3 more kilometers beyond that. You are now 4 kilometers from the basketball sun. If you started at one end of a small city, you would be approaching the other end just to reach the outer edge of the Kuiper Belt, and you have not left the solar system, not even close. Take a moment here. I know this is a lot to hold in your mind simultaneously. The basketball behind you, the marbles and ball bearings you passed, the 900-meter walk to Neptune, and now 4 kilometers total to the edge of the Kuiper Belt. Try to hold all of that in your body at once. Try to feel the whole model at the same scale. If you can hold that, if that is actually producing some kind of physical response in you, a sensation in your chest or your stomach, a kind of vertiginous opening outward feeling, that is what I want you to experience. That feeling is the correct response to the actual scale of where you live. That is your nervous system doing what it evolved to do when confronted with something genuinely vast and genuinely real. Let me know in the comments if you are feeling that right now. I genuinely believe that the ability to feel the scale of where we are is one of the most important and undervalued human experiences, and I want to know how many people watching this are having it. Now, beyond the Kuiper Belt, the Oort Cloud. If the Kuiper Belt is the outer suburb of our solar system, the Oort Cloud is the surrounding countryside, stretching to the horizon and beyond. It is the structure that, when you fully understand it, permanently changes your model of where the solar system ends. The Oort Cloud is not a disk like the Kuiper Belt. It is a sphere, a vast three-dimensional spherical shell of icy objects completely surrounding the solar system in every direction. Above, below, to every side, a bubble of frozen ancient material centered on the sun, extending outward for an almost unimaginable distance. The Oort Cloud is believed to begin at around 2,000 astronomical units from the Sun. That is 2,000 times the Earth-Sun distance, and it extends outward to somewhere between 50,000 and 100,000 astronomical units. Let me put that in context. The Kuiper Belt ended at 50 astronomical units. The Oort Cloud begins at 2,000 and extends to 100,000. The Kuiper Belt is to the Oort Cloud what a single room is to the continent the building sits on. On our scale, where the sun is a basketball and the Earth is a grain of sand 30 meters away, the Oort Cloud extends from roughly 130 kilometers to 650 kilometers from where you started. 650 kilometers. Stop and feel that. On the same scale that we use to place the Earth 30 meters from a basketball, the true outer boundary of the solar system is 650 kilometers away. That is the distance from New York City to Detroit, from London to Edinburgh and halfway back, from one side of Germany to the other, from Los Angeles to San Francisco and halfway back. That is our solar system. Not the 8 planets, not the Kuiper Belt. This 650-kilometer bubble of stuff gravitationally bound to our sun, most of it invisible and unmeasured and cold and silent and sitting in a darkness so complete it makes the darkness between the planets look like twilight. What is in the Oort Cloud? Trillions of comets, ancient city-sized snowballs made of ice and rock and organic molecules drifting in the dark at temperatures just a few degrees above absolute zero, rotating slowly, waiting. Most of them will wait forever. They will drift in the outer dark until the sun burns out and beyond, never disturbed, never moved, just sitting in the silence at the edge of the solar system for billions and billions of years. But sometimes something disturbs them. A passing star, a gravitational ripple from a distant galaxy, the cumulative tidal pull of the Milky Way itself slowly tugging at objects on the fringe. And when something disturbs one of these ancient snowballs, it begins to move. It begins to fall inward toward the sun. Slowly at first, barely perceptible, accelerating over centuries, and then millennia, as gravity reaches across the void to pull it closer. The journey of a long-period comet from the Oort Cloud to the inner solar system takes tens of thousands of years. During that journey, civilizations have risen and fallen on the grain of sand it is approaching. Languages have been invented and gone extinct. Ice ages have come and gone. The shape of coastlines has changed. Mountains have eroded perceptibly. And the comet keeps falling, silently, through the dark, closer and closer to the heat it has never felt before. And then it gets close enough to the sun that the ice begins to sublimate. The frozen surface starts turning directly from solid to gas, releasing jets of material that form the glowing coma and tail we see from Earth as a comet. Suddenly, this ancient frozen object, this relic of the solar system's birth, is visible across 1 billion kilometers, blazing briefly across our sky before falling back outward on its long journey into the cold. Every comet you have ever seen in your life made that journey. Every one. Halley's Comet, Hale-Bopp, the comet your grandparents saw, the comet your great-great-grandparents saw. Every one of them was an ancient Oort Cloud object that something disturbed, that fell for millennia through the dark before lighting up briefly in the sky of the grain of sand. I find something deeply moving about that. There is something in the image of an ancient frozen object falling for 20,000 years, through perfect silence toward the only warm light in an incomprehensible void, and then blazing briefly before going dark again. That feels like a kind of poetry that the universe wrote before there was anyone to read it. Okay, I want to check in with you again here. How are you doing? This is a long journey, and I do not want to lose you in abstraction. Tell me in the comments where you are right now. Are you still engaged? Is the scale building for you? Is there a specific image or comparison that landed hardest so far? I read everything, and I use what people tell me to make these journeys better. Your response genuinely shapes what I make next. Now, let us talk about Voyager 1. Voyager 1 is a spacecraft launched in September 1977. It is 49 years old at the time this video is being made. It was built with 1970s technology. The computer on board has roughly 68 kilobytes of memory, less than a single text message, less than a tiny fraction of a single photograph on a modern phone. And that spacecraft is still flying. Right now, as you watch this, Voyager 1 is out there in the dark, flying away from the Sun at about 61,000 kilometers per hour. It has been flying continuously for nearly 5 decades. It has covered more distance than any other human-made object in history. And it is still sending back data. Its signal, traveling at the speed of light, takes more than 22 hours to reach Earth. 22 hours for a signal moving at the speed of light to cross the distance between us and Voyager 1. Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in 2012. It entered interstellar space, the space between star systems, making it the first human-made object to do so. It is now in the void between our solar system and the next one. On our scale, Voyager 1 is currently about 16 kilometers from the basketball sun. 16 kilometers. After nearly 50 years of flying at 61,000 kilometers per hour, our most distant spacecraft is 16 kilometers from the basketball on our model. It has not yet reached the inner edge of the Oort Cloud, which begins at 130 kilometers on our scale. Voyager 1 will not reach the inner edge of the Oort Cloud for another 300 years. It will not fully exit the Oort Cloud for another 30,000 years. I want you to sit with that for a moment. The most distant object humanity has ever created, flying for 50 years at 61,000 kilometers per hour, has covered 16 kilometers on a scale where the true edge of our solar system is 650 kilometers away. The fraction of the journey it has completed is so small that if you walked from London to Edinburgh, Voyager 1's progress would be about the length of your stride. This is what it means to live inside something as large as a solar system. This is why interstellar travel is not just an engineering challenge. It is a challenge that calls into question whether the word travel even means what we think it means when you apply it to these scales. When we say travel between stars, we are not talking about a long flight. We are talking about something that requires an entirely different relationship with time and distance and the human lifespan. We are talking about something that, with our current technology, is not possible in a single human lifetime for even the nearest star. Let us talk about that nearest star, because we have spent a long time in the solar system, and now it is time to step outside. The nearest star to our Sun is Proxima Centauri. It is a red dwarf star, smaller and cooler and dimmer than our Sun, part of a 3-star system called Alpha Centauri that is the closest stellar system to Earth. Proxima Centauri is the closest of the 3, sitting at a distance of approximately 4.2 light-years from us. 4.2 light-years. Light travels at approximately 300,000 kilometers per second. In 1 year, light covers about 9,500 kilometers. 4.2 light-years is roughly 40 trillion kilometers. 40 trillion kilometers. 40,000 billion kilometers. 40,000 billion kilometers. You live 4.2 light-years from the nearest other sun. Now on our scale, where the sun is a basketball and the Earth is a grain of sand 30 meters away, and Neptune is a ball bearing 900 meters away, and the edge of the solar system is 650 kilometers away, where is Proxima Centauri, another basketball, sitting on the ground, approximately 4,200 kilometers from where you started, 4,200 kilometers, on the same scale as everything else we have been walking through. On the scale where Earth is a grain of sand 30 meters from a basketball, the nearest other sun is 4,200 kilometers away. That is the distance from London to Tehran, from New York to Los Angeles and past it to the Pacific, from Moscow to Beijing, from one major civilization to another on the other side of a continent. And between those two basketballs, between our Sun and Proxima Centauri, on our model, there is nothing. I do not mean very little. I do not mean sparse. I mean nothing. No planets on our model, no dust visible to the naked eye, no gas you could detect without instruments, just 4,200 kilometers of empty nothing between two basketballs. In real space, that nothing is 40 trillion kilometers wide. It takes light 4.2 years to cross it. If you drove a car at highway speed continuously without stopping, never sleeping, never resting, it would take approximately 48 billion years. The universe itself is only 13.8 billion years old. You would need to wait for the universe to age by 3.5 times its current age to cross the gap between stars at highway speed. This is what the silence between stars actually is. This is the physical reality of the void. This is why, when we talk about visiting other star systems, we are not talking about a technological challenge, the way going to Mars is a technological challenge. We are talking about something that requires either a completely different relationship with time, either extremely long lifespans or multi-generational ships, or some form of suspended animation or some physics we currently do not understand. Or we are talking about something that simply does not happen, something that is not on the menu for biological creatures with human-scale lifespans. And Proxima Centauri is the close one, the nearest one, the easy one if easy means anything in this context. The second closest star system after Alpha Centauri is Barnard's star, about 6 light-years away, then Wolf 359, then Lalande 2E18 2011A5, then Sirius, the brightest star in the night sky other than the Sun, about 8.6 light-years away. Each of them is a basketball thousands of kilometers away from our basketball, with 4,000 to 10,000 kilometers of absolute nothing between them. The sky is full of stars. On a clear night far from city lights, you can see a few thousand of them with the naked eye. They look close together. They look arranged almost, like they have some kind of structure. Our ancestors drew lines between them and saw shapes and told stories. But those stars are not close together. They are all basketballs separated by thousands of kilometers on our model. The night sky that looks so dense with points of light is the most misleading image in the history of human visual experience. What looks like a crowded field is, at the scale we have been walking, a vast empty countryside with one basketball every several thousand kilometers. Space is not what it looks like from Earth. It is not what photographs show you. It is not what the diagrams convey. It is something that the human visual system is completely incapable of representing accurately, because the human visual system evolved to function at scales that are 20 to 30 orders of magnitude smaller than the distances we are talking about. I want to ask you something here, and I want a real answer in the comments, not a comfortable answer, a real one. When you think about the gap between stars, the 4,200 kilometers between basketballs on our model, the 40 trillion kilometers in real space, do you feel trapped or do you feel free? Do you feel like the scale is a prison, something that locks us here on this grain of sand forever? Or does the immensity of it feel like something else? Like an invitation, like evidence that the universe is so much larger than our problems that our problems become smaller in proportion? I have asked this question in various forms to people over the years, and the answers split almost exactly down the middle. And I find that split fascinating. The same physical reality produces opposite emotional responses in different people. The same void either closes in or opens up. I want to know which it is for you. Now, let us zoom out further. We have been talking about stars as individual points, individual basketballs, separated by thousands of kilometers on our model. But stars do not float alone in empty space. They are organized, gravitationally bound into enormous structures called galaxies. And the galaxy we live in is called the Milky Way. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number is not a failure of measurement, but a reflection of how difficult it is to count stars in a galaxy you're inside. We cannot step outside the Milky Way and photograph it from a distance the way we can photograph other galaxies. We are inside it, embedded in one of its spiral arms, looking out through layers of gas and dust that block our view of much of the galaxy. So we estimate, and the estimate is 100 to 400 billion stars. The Milky Way is a spiral galaxy, a rotating disk with spiral arms extending outward from a central bulge, with a supermassive black hole at its very center called Sagittarius A star. The disk is roughly 100,000 light-years in diameter. Our solar system is located about 26,000 light-years from the center, roughly halfway out from the middle, in a region between two of the main spiral arms called the Orion Arm or the Orion Spur. On our scale, where Proxima Centauri is 4,200 kilometers from the basketball sun, the Milky Way galaxy is approximately 420 million kilometers across. That is roughly the distance from the Earth to Jupiter in real space. The entire Milky Way, 400 billion stars, mapped at the scale where Earth is a grain of sand 30 meters from a basketball, is about the width of the real distance from Earth to Jupiter, which means our scale is now completely useless. We cannot hold the galaxy and the solar system in the same frame. The numbers have diverged too far. We are not dealing with a difference of a few zeros. We are dealing with a difference of 8 or 9 or 10 orders of magnitude between the scale of the solar system and the scale of the galaxy. This is one of the most important things to understand about the universe. There is no scale at which both individual planets and galaxies fit comfortably in the same human intuitive frame. You have to choose. Either you zoom in until you can see planets, in which case galaxies are incomprehensibly large, or you zoom out until you can see galaxies, in which case planets are invisible specks. The universe operates across so many orders of magnitude that no single scale can make it all feel real simultaneously. And this is the cognitive vertigo at the heart of understanding the cosmos. It is not that the universe is too large to think about. It is that it requires you to think at multiple scales simultaneously, and human cognition evolved to operate at roughly one scale, the scale of a human body moving through a human environment. Everything else is abstraction, beautiful, important, mind-expanding abstraction, but abstraction nonetheless. Even the model we have been using tonight, the basketball and the grain of sand, is an abstraction, a useful one, a felt one I hope, but still a reduction of something that resists reduction. Let us talk about what is between the stars and why it is not actually nothing, even though it is almost nothing. The space between stars is called the interstellar medium. It is not a true vacuum. A true vacuum would contain literally nothing, no particles, no radiation, no fields. The interstellar medium contains all of those things, but in incredibly dilute form. In the densest regions of the interstellar medium, the giant molecular clouds where new stars are forming, there are about 1 million molecules per cubic centimeter. That sounds like a lot until you compare it to the air you are breathing right now, which contains about 27 million billion molecules per cubic centimeter. The densest part of the interstellar medium is roughly 100 billion times less dense than the air around you. In the typical interstellar medium, the average density is about 1 atom per cubic centimeter, a single atom floating in a cubic centimeter of space, waiting for the next atom, which might be a centimeter away, or a meter away, or many meters away. And in the void between galaxies, intergalactic space, the density drops to about 1 atom per cubic meter. 1 atom, one lonely particle of matter floating in a meter-wide cube of emptiness. And yet even this near-perfect void is not nothing. It is threaded through with magnetic fields. It vibrates with gravitational waves, ripples in space-time itself, emanating from colliding neutron stars and merging black holes thousands of light-years away. It is filled with cosmic rays, high-energy particles traveling at nearly the speed of light, accelerated by supernovae, and active galactic nuclei, streaming through everything, through the void, through planets, through your body. Right now, as you watch this, several cosmic rays are passing through your head every second. You cannot feel them. They mostly pass through without interacting with anything. But they are there, and most pervasively, the void is filled with the cosmic microwave background. This is the afterglow of the Big Bang itself. The universe in its first moments was hot and dense, so hot and dense that light could not travel freely through it. Then, 380,000 years after the Big Bang, the universe had expanded and cooled enough that electrons and protons could combine into neutral hydrogen atoms for the first time, and suddenly light could travel freely. That light has been traveling ever since, for for 13.8 billion years, and it is still everywhere. Every cubic centimeter of the observable universe contains on average about 411 photons from the cosmic microwave background. Right now, in the room you are sitting in, there are about 400 cosmic microwave background photons per cubic centimeter passing through you. They are the oldest light in the universe. They carry information about the state of the universe 380,000 years after it began. They are in your eyes right now, and you cannot see them because they have shifted to microwave wavelengths, far below what human eyes can detect. The void is not empty. The void is full of the history of the universe, written in frequencies we cannot see. Now, I want to take you somewhere most space content never goes. I want to take you to a question that I think is the most important unanswered question in the history of science. Where is everyone? The universe is 13.8 billion years old. Our solar system is 4.6 billion years old. There has been time, enormous quantities of time, for other civilizations to arise and develop and expand and communicate. The galaxy contains 400 billion stars. A significant fraction of them have planets. A significant fraction of those planets are inhabitable zones. The chemistry of life, amino acids, organic molecules, the building blocks, is found everywhere we look, in comets, in asteroids, in interstellar dust clouds. The ingredients for life are common, so where is everyone? This is the Fermi paradox, named for the physicist Enrico Fermi, who raised it in a casual conversation over lunch in 1950. Given the age of the universe and the number of stars and the prevalence of the chemical building blocks of life, statistically, intelligence should have arisen elsewhere many times. And given enough time, an intelligent civilization should eventually develop technology that allows it to expand or at least communicate across interstellar distances. And we should see or hear evidence of this by now. But we hear nothing, no signals, no visitors, no megastructures visible around distant stars, though we have looked. No obvious signs of large-scale engineering anywhere in the galaxy, just silence. The silence of a universe that looks, statistically, like it should be full of conversation, but sounds, observationally, like it is completely empty. The proposed solutions to the Fermi paradox are numerous and range from the comforting to the deeply unsettling. The rare Earth hypothesis suggests that the specific combination of factors that allowed life to arise on Earth is so improbable that it has happened only once or a handful of times in the observable universe. The right size star, the right kind of orbit, the presence of a large moon to stabilize the axial tilt, the right mix of elements, the right series of extinction events to drive evolution in productive directions, the right timing. The suggestion is that life, and especially complex intelligent life, is incredibly rare, possibly unique to Earth, not because the universe is hostile to life, but because the chain of necessary coincidences is so long that it almost never completes. The Great Filter hypothesis proposes that there is some barrier in the development of civilizations that almost nothing gets past, some step in the evolution from chemistry to biology to intelligence to technology to interstellar presence that is so difficult that civilizations almost universally fail at that step. The frightening question this raises is whether the Great Filter is behind us or ahead of us. If it is behind us, if the hard step was, say, the origin of life or the development of eukaryotic cells, then we got through it and we are probably rare and probably safe. But if the Great Filter is ahead of us, if civilizations routinely develop technology and then destroy themselves with it before reaching the stars, then we are approaching the filter right now, and the silence around us is the silence of a graveyard. The zoo hypothesis suggests that there are other civilizations out there, but they have chosen not to contact us. Perhaps they are watching. Perhaps there is a galactic community that has agreed to leave young civilizations alone until they reach some threshold of development. Perhaps we are a nature preserve. Perhaps they are waiting to see what we do. The timing argument suggests that we might simply be early. The universe is 13.8 billion years old, but the elements necessary for life, carbon, oxygen, nitrogen, iron, did not exist in abundance until a few generations of stars had lived and died and scattered their contents through the galaxy. We might be among the first civilizations to arise after the conditions for life became widespread. The conversation might not have started yet, We might be the first ones to show up to a party that will eventually be crowded. And then there is the possibility that no proposed solution has captured yet, that the answer to the Fermi paradox is something we have not thought of, something outside our current conceptual frame, something that will seem obvious in 1,000 years the way evolution and germ theory and quantum mechanics seem obvious to us now, but were invisible to everyone who came before. I have spent a long time thinking about the Fermi paradox. I do not have an answer. No one does. But I want your answer. Not your intellectually hedged, academically cautious answer. Your gut answer, the one that feels true to you when you sit with the silence long enough. What do you think the silence means? Drop it in the comments. I will read every single one. This question deserves more conversation than it gets, and I want this comment section to be a good one tonight. Let us go further out. The Milky Way is not alone. It is part of a local cluster of galaxies called the Local Group. The Local Group contains more than 50 galaxies, most of them small dwarf galaxies orbiting the two largest members, which are the Milky Way and the Andromeda Galaxy. Andromeda is a spiral galaxy similar to the Milky Way, containing perhaps 1 trillion stars. It is about 2.5 million light-years from us. On our basketball and grain of sand scale, Andromeda is so far away that the model breaks down completely. The Local Group is itself part of a larger structure called the Virgo supercluster, which contains about 100 galaxy groups and clusters spread across a region about 110 million light-years across. And the Virgo supercluster is part of a still larger structure called Laniakea, a vast supercluster of galaxies about 500 million light-years across, containing approximately 100,000 galaxies, including our own. Laniakea is one of many such structures in the observable universe. The observable universe, the portion of the universe from which light has had time to reach us in 13.8 billion years, contains an estimated 2 trillion galaxies. 2 trillion, 2 million, each one containing billions or hundreds of billions of stars, each one potentially containing hundreds of billions of planetary systems. 2 trillion galaxies. If you tried to count the stars in the observable universe at 1 per second, it would take longer than the current age of the universe to finish. Not by a little. By many, many orders of magnitude. The number of stars in the observable universe is estimated to be around 10 to the power of 24. That is a 1 with 24 zeros after it. That is approximately the number of grains of sand on all the beaches on Earth multiplied by 10 million, and the observable universe might not be the whole universe. There is a critical distinction between the observable universe and the universe itself. The observable universe is defined by a practical limitation. It is the sphere centered on Earth from which light has had time to reach us since the Big Bang. But the universe itself, the actual total extent of space and matter, might be vastly larger. Some models of cosmology suggest it is finite, but much larger than the observable universe, perhaps thousands of times larger. Other models suggest it is infinite, truly, properly, actually infinite, not very large, not larger than we can measure, infinite. An infinite universe would contain everything that is physically possible, infinitely many times. In an infinite universe, there are infinitely many Milky Way galaxies, infinitely many solar systems like ours, infinitely many planets like Earth, and infinitely many people like you sitting in rooms like yours watching videos like this one. In an infinite universe, nothing is unique. Everything recurs. Every arrangement of matter that is physically possible exists somewhere and exists infinitely many times, including every variation of you. Every version of you that made a different choice, every version of you that lived a different life. The mathematician in me finds this idea compelling. The poet in me finds it somewhat melancholy, because if everything exists infinitely, then nothing is special in the cosmic sense. The love you feel is somewhere being felt by an infinite number of identical versions of you. The grief you carry is being carried by infinite copies. The experience that defines you exists at this moment in infinitely many other places. But then again, maybe that changes nothing. Maybe the experience is still real. Maybe the fact that an infinite number of identical situations exist does not diminish any particular instance of them. Maybe the copy does not dilute the original. Maybe the love is still love, and the grief is still grief, and the meaning is still meaning, regardless of how many other instances of it exist somewhere in an infinite universe. I am genuinely not sure. This is the kind of question I sit with at 3 in the morning, and I am not sure anyone has a satisfying answer to it yet. What do you think? Comment below. Genuinely, now I want to slow down and bring us back toward Earth. Not physically. We have been covering conceptual ground, and I want to cover a different kind of ground before we finish. The kind that I think actually matters most. We have established the scale, the basketball and the grain of sand, the 30 meters to Earth and the 900 meters to Neptune and the 650 kilometers to the Oort Cloud and the 4,200 kilometers to the nearest star, and incomprehensible distance to the center of the galaxy and the 2 trillion galaxies and the possible infinite universe. Now I want to talk about what all of this means. Not in a grand, philosophical, abstract way. In a personal way. In the way that I think actually changes how a person lives after they have truly sat with the scale. Because I think the scale of the universe is one of the most misused facts in all of human discourse. People use it to make life feel meaningless. They say things like, we are just a pale blue dot, or we are insignificant specks. And the implication is that the scale of the universe makes human life and human experience and human meaning unimportant. The universe is so large, the argument goes, and we are so small, that we might as well be nothing. I think this is completely wrong. Not philosophically wrong, physically wrong. Here is what the scale of the universe actually shows us. It shows us that the universe had to be this big to produce us. The universe has to be roughly 14 billion years old for there to be stars old enough to have produced the heavy elements that life requires. Stars like the Sun need billions of years to form and burn and die and scatter their contents before new stars with rocky planets can form. And then those rocky planets need hundreds of millions of years for the chemistry of life to get started, and then billions more years for that chemistry to evolve into something complex enough to look at the sky and ask questions. The universe could not be young and also contain us. It had to age. It had to be vast. It had to run through billions of years of stellar evolution and billions more of planetary evolution before the conditions existed that allowed a nervous system to form that was complex enough to feel wonder at the scale of the space it inhabited. The size of the universe is not evidence of our insignificance. It is the minimum size required to make creatures who could notice the universe in the first place. You are not small relative to the universe. You are the size you need to be to do what you do. You are made of atoms that were forged in the cores of dying stars. The carbon in your cells was created in the triple alpha process inside red giants. The calcium in your bones was scattered by stellar explosions. The iron in your blood was created in supernova cores, the most violent events in the history of the universe. You are not separate from the universe and looking at it from the outside. You are a local arrangement of the universe looking at itself from the inside. And that looking matters. That awareness, that capacity for wonder, that ability to build a model of reality and feel awe at what the model reveals is the rarest thing we know of. We have surveyed thousands of planets. We've listened for signals from the cosmos for decades. We have searched for signs of large-scale engineering, for atmospheric biosignatures, for anything that would suggest that the capacity for wonder is not unique to this grain of sand. And so far we have found nothing. So far as we can tell, the entire observable universe contains exactly one place where matter has organized itself into something capable of understanding the universe. One grain of sand out of more than 1 billion trillion potential grains of sand. One place where the atoms that were scattered in the Big Bang have arranged themselves into eyes that can look at the stars and brains that can feel something about what the eyes see. That is not nothing. That is the most remarkable thing we know of in the universe. And you are part of it, not peripherally, not as a spectator, as the actual substance of it. You are made of the universe, looking at the universe, understanding the universe, feeling things about the universe. You are, in the most literal physical sense, the universe becoming aware of itself. The grain of sand is remarkable not because of its size, but because of what grew on it. Let me bring us to the question of time one more time before we close, because the time scale is, if anything, more difficult than the space scale, and I think it deserves its own moment of attention. We have been talking about distances. Cosmic distances are so large that we measure them in light years, the distance light travels in 1 year. But the universe also operates across time scales that are as incomprehensible as the space scales. And these two incomprehensibilities compound each other. The Sun formed 4.6 billion years ago. Before the Sun, there were other stars. Stars in the same region of the galaxy, burning through their hydrogen, creating heavy elements in their cores, exploding as supernovae, scattering their contents through the galaxy. Those elements, that carbon and oxygen and nitrogen and iron, drifted through the interstellar medium for millions of years before the gravitational perturbation of a nearby supernova triggered the collapse of the cloud of gas and dust that would become our solar system. When the Sun ignited and the planets formed and the Earth settled into its orbit, the building materials of the Earth were already ancient. The atoms in your body have been in existence for as long as the universe has been in existence. They have been through multiple stellar cycles. They have been inside stars and scattered through space and gathered into planets and dissolved in oceans and incorporated into the chemistry of life many times before they found their current arrangement inside you. You are made of atoms that are as old as time, and those atoms have been doing things, cycling through the universe, becoming stars and gas and dust in oceans and organisms and eyes and nervous systems and brains capable of looking at the sky and wondering. For the entire history of the universe, your atoms were there at the beginning. They have seen everything the universe has done. They carry within them, encoded in their physics, the history of everything that has happened since time began. They are old beyond any measure of old that human intuition can access. And they are here now, arranged in this specific configuration, reading these specific words, feeling whatever you are feeling right now. That will only happen once. However many copies of you exist in an infinite universe, this particular arrangement in this particular room at this particular moment is unique. Even in an infinite universe, the specific subjective experience of this moment is local. It is yours. It exists here and only here, in this specific configuration of atoms that is you right now. That specificity matters. That localness is not an illusion produced by a finite brain. It is the real texture of experience, and no amount of cosmological scale can dissolve it. You are vast, and you are tiny. You are ancient, and you are new. You are made of the oldest things in the universe, and you are using them to do something they have never done before. You are one arrangement of the universe that will never exist again in exactly this form. And you are spending some of that finite, unrepeatable time looking at the scale of the void. I think that is time well spent. Before I let you go tonight, before we close this journey, I have one last question. And I want it to be the question that carries out of this room and into the rest of your life. If you could send a message to whatever might be out there, to whatever intelligence might be listening in the void between the stars, to whatever consciousness might exist on a grain of sand somewhere in one of the 2 trillion galaxies we can see, what would you say? Not a scientific message, not coordinates or mathematics, just words, human words. What would you want the universe to know about what it is like to be here on this grain of sand at this moment, with this brief and precious arrangement of atoms that you call yourself? Leave it in the comments below. I will read every single one. I have been reading comments on videos like this for years, and the answers to that question are some of the most beautiful things I have ever read. Some of them have changed the way I think about what we are doing here. I want to see what this specific group of people who have come this far through the dark tonight wants to say to the void. And if this journey gave you something tonight, if the scale landed differently than it has before, if something shifted in how you understand where you are, share it. Not because the algorithm needs it, though if you want to support what we do here and keep these journeys coming, subscribing and hitting the bell genuinely helps more than I can express. Share it because scale is something that changes people, and the world could use more people who have truly felt where they are. If this video moved you, if you want to support what it took to make it and what it takes to keep making these journeys into the dark, there is a super thanks button below. Every single one I receive gets read, gets a reply, and goes directly into the next journey. Your support makes this possible in a way that I am genuinely grateful for every time it happens. Sleep well tonight. Wherever you are on the grain of sand, in whatever city, in whatever room, in whatever moment of your life this video found you, you are exactly where the universe put you. You are made of stars, and you are surrounded by an incomprehensible void, and you are somehow aware of both of those things at once. That is remarkable. You are remarkable, and the void is very, very beautiful when you know how to look at it. Good night.